Hello, ladies and gentlemen. We're going to have an online lesson today dealing with theoretical probability, sample space, and complementary events. And we're going to talk about how we can visually represent a sample space a number of different ways. And we'll know we're successful when we can use visual representations to correctly identify the sample space of an event and find the theoretical probability of an event. To start with, we'll talk about the term sample space. Sample space is the set of all possible outcomes of an experiment, and we'll look at some examples of that coming up. There's three ways to do it. One is lists as a set. Whenever you make a list, you should have done this last year in Math Studies 1, you use these little braces, they're called. They're like the fancy parentheses, or gull wings as they're sometimes referred to, or squiggly parentheses, but braces is the official name of that. And then we'll talk about two-dimensional grids, and last but not least, tree diagrams. So to start with, we're going to make a list. So a list of the possible outcomes for tossing a coin. Now think about a coin, like a penny or a quarter or something like that. How many sides do we have? Well, two possible sides, and so that's the total of what we've got, and that's very similar to what we talked about in the last lesson, that anytime we write probability, we always need to think about the total things. Well, so there's two different things happening here. We could have heads, or we could have the tails, and if it's a single coin, those are the only possibilities. Now, if you think back to the last slide, anytime we make a list of something, we need to use those braces. And so right here, I have listed all the possible outcomes for tossing a coin, heads or tails, listed in the parentheses or the braces. And that is an example of a list of the sample space, only two different possible outcomes. Rolling a die, if it's a standard die, like a set of dice from a board game like Monopoly, we're going to have 1, 2, 3, 4, 5, or 6. A six-sided die has 6 different outcomes, so the sample space contains 1 through 6. Example 2, we want to illustrate the possible outcomes when both a coin and a die are thrown, and this time we're going to use a two-dimensional grid. Two-dimensional grids I don't use as often in class as maybe some of the others, especially like a tree diagram, but they can be useful especially when you have two different things happening. Now let's think about it. What are the two things that we have happening? Well, the first one is a coin. Well, what could happen on a coin? Well, we just talked about that on example 1. A coin could either be heads, heads, or it could be tails. And then the other thing that's happening, and this was what's going to make it into a grid, is that a die is thrown. All right, so I'm going to make another axis, if you will, and I could have on the die a 1, 2, 3, 4, 5, or 6. Now, all I've done is just make an X and a Y axis here. In order to make a grid, we have to actually do some connecting. So I'm going to extend this one here, extend that one there, so on and so forth. And then do the same thing here with all my options. And everywhere they intersected, 1, 2, 3, 4, so on and so forth, those are all of the different outcomes of this sample space. So we could have a head with a 6, which happens right here. Or you could have a 1 with a tail, which happens right here. And then again, you could have a 2 with a tail and a 3 with a tail and so on and so forth. But the places where they intersected, all these different dots here, are a total of 12. So there's 12 different things. And that's an example of a two-dimensional grid. Again, 2 dimensions, an X direction and a Y direction. If I had 3 things going on, like flipping a quarter, rolling a die, and flipping a penny as well, I wouldn't be able to do it with a grid because too many dimensions. Now we're going to talk about a tree diagram. Tree diagrams are very useful. They seem a little tedious at first, but they're probably the most useful when you get to more complicated problems. So we're dealing with the same thing that we had before. There's 2 events that are happening, 2 actions. It says illustrate the possible outcomes when a coin and a die are thrown. So we're doing two things. We're throwing a coin. So I'm going to write that down first. And then we're doing one other thing, which is rolling or flipping a die. Again, part of a dice, a six-sided cube. And that's the first thing you need to do. You need to make labels. And I just horizontally did that. I've got the coin, I've got the die. And now we're doing a tree diagram. Think about, how does a tree grow? Well, the first thing that needs to happen is a seed needs to plant. And so we're going to plant our seed over here on the left. And then from our seed, different branches will grow. Well, for a coin, what are our different outcomes? Well, a coin could be heads, or a coin could be tails. And those are the only two outcomes. So for a coin, notice looking right below the coin here, I've got my two options of heads and tails. You don't have to circle them. I'm just showing you with that. And that's it. Now, from each one of those options, I'm going to split out again to a die. Now, what could a die be? It could be 1 through 6. 1, 2, 3, 4, 5, 6. Notice I listed those directly below die, and the heads could go to the 1, to the 2, the 3, 4, 5, or 6. And then the same thing could happen with tails. It could also spread out to 1, 2, 3, 4, 5, 6. Now, some students say, do I need to write the 1 through 6 again? Yes, you do. Because now I can look under the die, which was my last event that happened. I first flipped the coin, then I rolled the die, and I can see that I have 1, 2, 3, 4, 5, 6 here, and then another 6 there, meaning there were 12 different outcomes. The heads with the 1 through 6, and then the tails with the 1 through 6. Again, very simple example. It takes a little space on the paper, and that's an example of a tree diagram. Now we're going to look at a more complicated one. This time I've got two different coins, as I was talking about earlier. I've got a penny, a nickel, and a die are being thrown, and we want to show that with a tree diagram. If you haven't tried it on your own yet, this might be a good time to pause the video and give it a shot. Leave yourself some space to do this. All right, so we think about what are our events or actions that are happening. We've got the penny, we have the nickel, and then, of course, we have the die. Always label those actions first, and then from there, plant your seed. So starting with my seed, I think about what could happen for the penny. It could be heads or it could be tails. I'm just going to abbreviate with H and T for now. And then from there, we're moving on to the nickel. Well, a nickel could be heads or it could be tails, but I need to branch out from every previous branch just the way a tree does. Tree doesn't just grow one set of branches and then, continue out there. It'd be lopsided. It's got to keep spreading. And then last but not least, we have to think about the die. And unfortunately, the die has 6 options. So 1, 2, 3, 4, 5, 6. I'm probably going to run out of room here, but maybe I can squeeze it in. And then the tail, 1, 2, 3, 4, 5, 6. And then we have the same thing coming off of the penny tails. Heads on the nickel, 1, 2, 3, 4, 5, and 6. Let's squeeze that in up there. And last but not least, tails, 1, 2, 3, 4, 5, and 6. And I tried to keep that relatively organized. I got a little bit squished over there. But we can see 1 through 6 continues here, and then again here. So that's 12, 18, and then finally 24. 24 different options, and I can visually see what each and every one of them are. Eventually, we're going to throw some numbers in here. Maybe it's a lopsided coin, and there'll be a different probability for getting a heads versus getting a tails, and we'll expand on that. But for now, we're just making these pictures. All right. When we talk about theoretical probability, it's different from last lesson where we had experimental probability or observed probability, where you actually saw what happened. For theoretical probability, it's all done sort of in your head. It's the way gamblers think about things. They might think that there's a good chance that they'll win. It doesn't mean that they still will or won't. It's just we're looking at the chance. So the theoretical probability of a particular event is the measure of a chance that that event will occur in any trial of the experiment. It's not meaning that we're recording the experiments. It's saying our expectancy that that might happen. So we often use this notation right here, P parentheses E. It doesn't mean P times E. It means the probability, so the P will always be used, of an event E occurring. For example, if I was talking about the coin again, and I would say the probability of getting heads on my coin is equal to maybe 1/2, 1 out of 2. So that would be the example of that notation. Or the probability of spinning yellow on my spinner might be something like that, and maybe it's a 1 out of 4 chance that I would have there. So that's what the notation looks like. Now, what do these numbers mean? We've got the probability of getting heads on a coin, we said, is like 1/2. Well, probability is a range of values that goes from 0 all the way to 1. The lowest value you could possibly have is 0, and the biggest one you can have is 1, and any number in between. Now, those could be expressed other ways using decimals. You can have probability as a decimal between 0 and 1, or fraction, or you can use percents, which means between 0 and 100%, because 100% is one whole. If you have 0, what that means is it's not going to happen, will not happen. No chance. And if you have 100% or a 1, that means it will happen. It's guaranteed. It's a sure thing. And in the middle there, we might have like a 1/2 or a 0.5 or a 50%. And that means it's well, a coin flip. It happens half the time. It's likely to happen about half the time. It doesn't guarantee it'll happen, but that's theoretically half the time. And then everything else between here, numbers like 0.6, 0.7, 0.9, 3/4, 3/5 even, these are all numbers that are bigger than a half, and they are more likely to occur. Doesn't guarantee they will, but if you had to bet, that's where the best bet is. They're most likely to occur. And then over here between 0 and 1/2, they're less likely to occur. Again, it doesn't mean that it can't happen, but it's just less likely to happen. And that's really what probability is all about. It's just a measurement on how likely we think something is to happen. So again, this probability of heads, that happens about half the time. Probability of getting yellow on a spinner, in this particular case, happens 1 out of every 4 spins, so it's less likely to occur. Now we've got a term called complementary events. Complementary, it's not like giving a compliment saying you look nice today. It's sort of like an opposite, or better yet, it's everything else that we're not talking about. So if I say an event is it's sunny outside, the complement is everything else. It's not sunny outside, meaning it could be rainy, it could be cloudy, it could be snowing, all these sorts of things. And the way we illustrate that is we take whatever the event is and we put a little tally next to it. It's like a prime symbol, E tally. It's not a 1, you'll notice that it's at a slant, but just a little prime, and that's what we call that symbol, prime. So E prime means not E, so the complement of it. And so if I know the probability of E, let's say it was 30% would happen, or 0.3, then that means the probability of not happening is 70% of the time, or 0.7, and they always have to add up to 1. And I think they might show it like this in your formula packet or something similar to that. So if you're trying to figure out the probability of something not occurring, all you do is you take everything, 100%, 1, and you take away the probability that it will occur. Again, if something's going to occur, let's say it has a 3/4 chance of occurring, well, then I know that the probability of not occurring is 1 minus 3/4, which is equal to just 1/4. And that's how you can figure out a complement. They must add up to 1, though. Must add up to 1, always. I think we'll finish with this example, and any of the remaining ones on this slideshow we'll talk about in class. So I've got a 6B Math Studies class containing 34 students, of which 15 are boys. What is the probability that a randomly selected student is a boy? Second, what is the probability that a randomly selected student is not a boy? You can pause it and write these answers down now. Anytime we talk about probability, we need to know the total. And I think it's easiest to start off as a fraction. So for this first question, I need to think what is the total, and it contains 34 students, so I put 34 in the denominator, and then I put in the numerator my desired outcome. Well, for this first one, I want that student to be a boy. How many boys were there? There were 15. So my probability is 15 out of 34. You could also put that in a calculator and make a decimal or a percent, but I like it just like that as a fraction. The second part of the question, what's the probability that they're not a boy? Well, that's a complement. So all I have to do is take 1 minus 15 over 34. Or another way to say that is 34 over 34, which would be all the students, minus the 15 boys out of the total. I keep the same common denominator when I subtract, and 34 minus 15, I believe, is 19. And so there's a 19 out of 34 chance that the student is not a boy. And again, that's a little more than half, so it's a little more likely that the person would not be a boy rather than being a boy. And another way to say that is there's a 19 out of 34 chance that the person is a girl. For homework, we've got page 266, problem number 1, just parts A, B, and D. And then there's a bunch of parts for 2 and 3 that you should take a look at. Those are just about making sample space grids and tree tables or things like that. And then on page 268, some problems similar to the last example we did. Hopefully we are getting to the point of understanding the visual representations of a sample space and finding the theoretical probability of an event.